Hello everyone, and welcome to the NEATEC Electronics Series. This episode is about the bipolar junction transistor, so let's get started. Hello everybody. So I wanted to talk about the bipolar junction transistor. Now, specifically, the bipolar junction transistor comes in two flavors, and I've drawn them out here for you. One is called the NPN, right, which is right here. And as you can see, you have an N here, P in the middle, and an N-doped region here. So NPN, the N stands for a negatively doped region, P stands for a positively doped region. If you notice at this point, right there at that line, we have a PN junction, don't we? PN junction, right? Just call it PN junction right here. And if you notice right here, we have another one, don't we? Another PN junction, right? Well, each one of these regions is connected to an output. Now, for the NPN type of transistor, we have the collector here. That's what the C stands for. C stands for collector. B stands for base. And E stands for emitter. Alright, now that's pretty universal for the bipolar junction transistor. By the way, one thing I wanted to say, B, J, T, many times, instead of saying bipolar junction transistor, you're going to hear it's pronounced BJT. Right? That's the acronym for it. Now, the other flavor is right over here. It's the PNP. And you have a P-doped region, an N-doped region in the middle, and a P-doped region below. And again, have a PN junction here and a PN junction right here. Alright? Now, again, you have the collector here, right there. You have the base right here. And you have the emitter right here. Alright? So, what I did below here, that's pretty much how they're made. Somewhat. It's more how they're made than a schematic. So then below this line, I drew the actual symbol for it, okay? Again, if we're talking over here on the NPN N side, right? You have the collector, you have the base, and you have the emitter. This is the symbol. Usually, you may find a circle around it, you may not. Just be aware of that. But you have an arrow pointing away. That arrow pointing away is always your emitter. Okay? Just remember that. Right? The base comes in from one of the sides. Usually that's how they're made. Or usually that's how the symbols are, I'm sorry. And the collector comes from the top. The PNP, very similar. Collector, base, emitter. But notice the emitter. The arrow is pointing towards the junction, not away. So that's how you can tell the difference between a PNP and an NPN in a schematic diagram. Alright? Alright, so let's take this and let's discuss it further. So I'll be right back with another drawing. See you shortly. Alright, so I have redrawn the bipolar junction transistor, the BJT, in a circuit here. And the reason I did that is I want 2 points to come across to you. First off, this is an NPN transistor, right? And you can see that. Let me just draw it here. It's going to be NPN. PN. And how can you tell? That's an N, by the way. The arrow's pointing away, right, on your emitter. But the point is, in operation, all right, if you look at this, we have an independent voltage source here. And if you recall, you needed to have 0.7 volts across a PN junction for it to conduct. So you can think of this, if you recall, that was how the diode worked. This is basically a diode right here. Right here. That part with the arrow, the emitter, from the base to the emitter, BE, is basically a diode. And you need to have 0.7 volts at least across that for it to work. Okay? For it to conduct, I should say. So if you have a voltage here, you're going to have a resistor here, and you're going to have this diode right here. By the way, that's going to be termed VBE, and that is equal to 0.7 volts. In VBE, this terminology, this basically is VB minus VE. And you know, VE over here, this is your emitter right here. It's connected to ground. So this, in this circuit, is what? That's 0, isn't it? So this is saying that VB must equal 0.7 volts, right? So the point is, and we're going to do more problems discussing this, what we're just talking about right here. But for this to be an operation, this is forward biased. Get it? At the same time, though, we are that's this part right here. That's point 1. I wanted you to get that. The base to collector for operation. I'm sorry, I did the wrong one. Base to emitter right here. It's this one. I'm sorry. This one right here. Base to emitter is forward biased. Base to collector, if you notice, you're going to have a higher voltage on this side right here. It's going to be positive, much more positive than this. This is in reverse bias. Get it? And I put both of these right here in blue for you. So this was the other one I wanted to get across to you. That in operation, when this is in operation in a circuit, when it's being used in conducting, I should say, then this is going to have 0.7 volt drop across it, and this will be in reverse bias. All right? When I say this, the base to emitter junction right here will have 0.7 volts of a drop, and your base to collector will be in reverse bias mode. Alright? Alright, so now what I think I'm going to do is I'm going to draw a picture of a transistor, and I'm going to try to draw how this operates so you get a better understanding, and then you understand where the current comes from and where it goes. So again, see you shortly. Alright, hello everybody. So I redrew the BJT, Bipolar Junction Transistor, in an attempt to visually show what's taking place, okay? So in operation, if you notice, down here, let me move that over there. So you're right here is where I'm talking about. Your emitter region right here, that's very highly doped. Alright, there is a lot, or there are a lot, I should say, of electrons there. Okay, so it's a large density of conduction band free electrons available in this region, right? Now, when this is in operation, that means that there is a 0.7 volt. There's 0.7 volts between your base and your emitter. Remember, that's a diode, and these electrons need that voltage in order to have enough energy to overcome the barrier potential, right? So once they get in there, a small percentage go through your base as valence electrons and as hole current. And I tried to draw the holes here and the electrons going in one direction. Right, these are basically electrons going here. I drew the holes in blue in an attempt to show you what's taking place. But hole current, remember, takes place in the valence band, right? And an electron moves to where a hole is, and when an electron moves to where a hole is located, where it moved from, the electron leaves a hole. So the holes travel in one direction and the electrons travel in the other direction, okay? Now, when I said a small percentage, what I mean is basically 1 to 5%. Because if you look at what is happening to 95 to 99% right here, 95 to 99% of the electrons that cross this potential, this barrier potential, continue right here as I drew an arrow into your N region here. This is they see this positive potential and they continue moving right into this collector, which is a metal wire, right? So those electrons that leave the crystalline structure via the base, for talking about the base, become free electrons in the metallic base lead, right? And they produce your base current, right? But most of them move towards the reverse bias collector region and are swept into the collector region based on this potential right here, all right? And once in there, they're also going to move into the metallic lead and the metallic base lead and produce an external current as well, all right? So one thing to think about here is, if you'll think about it, your current, let me get the right thing here. So we have IE, your emitter current is going to equal your base current plus your collector current, all right? And we just said this is very small, right? It's like between 1 and 5% of the electrons are there. So take this route in the base. So basically we use an approximation, or an approximation is used, commonly used in our problems, where we say that the emitter current is approximately equal to the collector current, all right? So these two relationships you probably want to write down. It's an important thing to understand in understanding how we utilize equations to solve problems with the bipolar junction transistor, okay? All right, everybody, I'll be right back and I'll continue the discussion. See you shortly. Hello everyone. I redrew the circuit with a bipolar junction transistor in the middle, and what I did is I redrew the arrows pointing for conventional current flow versus electron flow. And electron flow is blue, and the conventional current flow is going to be red, okay? So what I just showed you, I showed you electrons coming up from the emitter towards the device right here, all right? Right here, up here, coming on in, and then I showed you a small percentage of them come out of the base, and the rest of them, 91 to 95%, continue on into the collector, okay? So I kind of made that arrow a little fat, sorry about that. I'll redraw that one for you. So they come right up here this way, all right? Now, when you put a BJT in a circuit, most times you don't use electron flow. You use conventional current flow. That is in red. So conventional current flow is simply the exact opposite of electron flow. So most times what you're going to see is just have a base current flowing this way right here, okay, and you're going to have an emitter current flowing out right here, and you'll have a collector current flowing in. So if you think of a rain gutter with water flowing, if you have water coming in from your base, you have water coming in from your collector, all of it's going to come out through your emitter. Water is a good way to think about electron current flow sometimes, all right? So again, those equations I wrote for you still hold, right? I of your emitter is going to equal I of your base plus I of your collector. I want to make sure that you understood this because you usually see it in the conventional current flow form. You don't see it in the electron flow form. Electron flow is very good for understanding the internal operations of what's taking place. But I just want to make sure that everyone understands the difference of what's happening. So when we're doing problems, the problems are going to be in conventional current flow, using conventional current flow. And I'll make sure if there's any difference, I will state that. Okay, everyone. Why don't we just continue here? So we have another thing to talk about. And this is called beta. And beta is going to equal what's going to be termed as your collector current divided by your base current. Remember, your base current is very small, right? Your collector current obviously is larger, right? So depending on the transistor that you're using, beta, by the way, I usually have draw with a little tail here, beta can equal, I'm going to put it, can equal, depending on the transistor, it can equal 50 to 200. I mean, it all depends on the transistor. Here is your amplification, all right? A small current going in your base can produce a large amount of current flowing in your collector and your emitter, all right? That's very important. There's another characteristic which I think you should be aware of, and it's called alpha. By the way, before we leave this beta, they have beta DC, which I'll write here, DC. They also have beta AC. Right now we're studying DC, so that's what we're going to use. But beta can be different depending on what kind of signal goes into your, is being fed into your transistor, all right, as well as the temperature, okay? So let's talk about alpha, which I was just talking about. Alpha DC is going to be equal to IC over IE. Your emitter, your collector current over your emitter current. Remember, your emitter current is the largest. And this is close. Remember, your collector, if you subtract the base current from your emitter, you get your collector current. So this is going to equal 0.95 to 0.99. This is where I got the 95% to 99% electron flow across the junction into the collector, right? It's this right here. 95 to 99% of the electrons that come in through the emitter are going to continue out through your collector. And if they don't go there, there's only one other place for them to go, and that's right here, out your base. Alright? Alright, so next I'm going to draw another transistor model for you that may help in your understanding. See you shortly. Alright everyone, so this is another representation of a bipolar junction transistor that is commonly used. If you notice here, you have your base right here. Here's your base right over here. Here's your emitter. Your VBE, your base to emitter voltage, is obviously across this diode. Remember, it's just a PN junction. So what we talked about, that's just a, what is it? It's a diode, right? Now you know what beta is, right? Basically, your base current times beta is going to equal, and put a little tail there, it's beta, is going to equal your collector current, right? So if what you have right here is that basic equation, that is your collector current. So this is a current source, if you're not aware of that. That's a current source. And the current source, the amount of current that's flowing, is controlled by beta and the amount of current coming in your base, right? And if you notice, they both go right to the emitter. So this is a good thing to have in your back pocket, just to understand that you will see this as we go through some problems in the future. Amplifiers are in some ways are good to help explain what's going on with this type of model. Alright? But I want to make sure that you are exposed to it and you see it and you know what it means. So let's just draw your current just for fun, right? Where your current for your base, conventional current flow, mind you, is going in this way, isn't it? And your current for your collector, I see, is going in this way, isn't it? Got it? Alright everyone, now we're going to get into some fun things where we're going to start to look at some equations that are trying to help you find different voltages and currents and things throughout the transistor model. See you shortly.